Hello. Any doubt from last class, Ifra?
No, sir.
Last class I defined you. If a hot body is placed in cold surrounding, so how much heat it will lose and how it is related with change in temperature of body and surround. So on this basis, let me define you Newton's law of cooling. It states when a hot body is placed in cold surrounding, the rate of heat lost by it is directly proportional to the temperature difference of body and surrounding. That is, the rate of heat lost is proportional to temperature difference between body and surrounding. So rate of heat lost is dq by dt. Since on losing heat, its temperature would decrease and final heat will be lesser as compared to its initial heat. So dq by dt will be negative, proportional to temperature difference of body and surrounding. So it will be T minus T naught. So if you replace this proportionality sign by any constant term, you will get dq by dt is equals to minus of C times T minus T naught, where C will have same, which is 4 epsilon naught sigma A T naught to the power 3. This will be the value of proportionality constant according to the above expression. Ifra, is it clear? Okay. Now, this particular heat will cause to change the temperature of that particular hot body. So we can say this loss in heat will cause to decrease the temperature. So dq equals to ms dt according to specific heat. So we may write in the above expression as dt by dt equals to minus of C divided by m into s multiplied by T minus T naught. So if you simplify this particular part, or you will say this dt by dt is nothing but rate of cooling or rate of decrease in its temperature. So this particular rate related to this formula will be inversely proportional to specific heat of that substance, that is S. So greater the value of specific heat of substance, it means the rate of cooling will be small and vice versa. Next, if we simplify this particular fraction, this equation to find temperature, dt divided by T minus T naught equals to let's say this is some another constant k multiplied by dt, integration. So on solving this, you will get log t minus t naught, which is equals to k and dt will be t. So if you plot graph variation related to this part, log of temperature T minus T naught. So let's say at initial, it will have some this value. So it will tend to decrease linearly like this, and slope of this particular curve from this point to this point will equals to K, which is 4 epsilon sigma A T naught to the power Q divided by M into S. So from this part, we can say this particular slope will depend upon two factors. First is specific heat constant. Second is epsilon, that is called emissivity of substance. So greater the slope of this particular curve, it means specific heat will be small and epsilon would be large, and vice versa, we can say. Ifra, any doubt?
No, sir.
Further, if you simplify this particular log, according to the expression, if you have ln x is equals to any natural number n, so x will be equals to e raised to n. So using this property, we may write t minus t naught equals to e raised to minus of k into t. So graph for this function will be exponentially decreasing like this. Just 1 minute. First, write it down to this part.
Okay, sir. Done, sir. Can you slide?
Now, for calculation purpose, since log will be difficult to solve, so let me define you shortcut method. As we had dt over dt equals to minus k times t minus t naught. This numerator dt is simply temperature difference. Suppose if a body is changing its temperature from some initial value to some final value. So its temperature will be T final minus T initial, and time T minus 0 is equals to minus some constant K. This T will be average Ti minus Tf divided by 2 minus T naught. Since final temperature will be smaller as compared to its initial temperature, so if you reverse this particular notation, there will be negative sign. That negative sign and this negative sign will cancel out. So you'll get Ti minus Tf divided by time taken equals to some proportionality constant K, average temperature Ti plus Tf divided by 2 minus T naught temperature of surrounding. So this is the formula to solve numerical on Newton's law of cooling. Let me define you question related to this part and how to solve. A body at 60 degrees Celsius is placed in cold surrounding of 10 degrees Celsius. In 5 minutes, its temperature become 40 degrees Celsius. Find time in which it may further fall to 20 degrees Celsius. In this part, we have a body initially at 60 degrees Celsius. Its temperature changes to 40 degrees Celsius and then to 20 degrees Celsius. In first part, time taken is 5 minutes, and second part, we have to calculate its time change. Temperature of surrounding is 10 degrees Celsius. So first, in this part, and second in this part, try to calculate. We have Ti as 60 degrees Celsius and Tf as 40 degrees Celsius. Time taken in this part is 5 minutes, that is 5 into 60, that is 300 seconds. Put this term in the above formula, you will get first equation. Similarly, write for the second part and just equate them to find the value of time taken in second process. Is it clear?
Okay. Yes, sir.
Try to solve. Good, Ifra. So in term of minute, it will be 10 minutes. So from this part, we can say initially it was at 60 degrees Celsius, changes to 40 degrees Celsius, and further to 20 degrees Celsius. So in first part, time taken is 5 minutes, but in second part, time taken is 10 minutes. But to change the temperature from this point to this point, and further from this point to this point, change in temperature in both processes same. So why there is a different time gap for same amount of change in temperature? So you'll say initially this pot is at higher temperature. On cooling down to 40 degrees Celsius, the rate of cooling of body will also decrease. That's why it will take a longer time to change by same amount of temperature. So we can say at low temperature, the rate of cooling of a body also decreases. So it will take longer time to change the temperature by same amount. So we may write at low temperature, rate of cooling of body decreases. So it will take longer time change the temperature by same amount. Now, you related to this concept, there was a question. Suppose you have a body at 100 degrees Celsius, changes to 90, changes to 80, and then 70 degrees Celsius. Let's say temperature of surrounding is 10 degrees Celsius. Time taken in first part is T1, second part is T2, and third part is T3. So how will T1, T2, and T3 be related with one another? Ifra, any idea?
So T3 will be largest and T1 will be smallest.
Good. So according to the above concept, at low temperature, rate of cooling of a body also decreases. So it will take longer time to change by same amount. So we can say at higher temperature, rates of cooling will be larger. So T1 will be least, then T2, and then T3. Okay, just write it down.
Okay, sir.
Okay. One last part of this chapter is Wien's displacement law. Suppose a body which having temperature, so it will have thermal kinetic energy due to temperature, that is 3 by 2 kBT. And every hot body which having temperature greater than 0 Kelvin will have tendency to emit and absorb electromagnetic radiation at all time. So if it radiate electromagnetic radiation, that electromagnetic radiation will be in the form of photon. So it will have energy as hc by lambda. So we can relate these two energy and we can say the rest of the thing is constant. So temperature and wavelength is inversely proportional to each other. From this relation we can say. So if a rod is placed over fire or suppose flame, which color do you observe first for this particular heating body? In which color it would radiate initially,
Red.
and then on further heating, whether there will be any change in temperature and any color, or it will tend to remain at rest, red.
So color changes.
To
So when I have seen it changes to blue.
blue. No. All of a sudden it won't change into directly blue.
Yes.
It may go through first orange, then yellow, and then so on. Then at last it will tend to blue. Let me define you reason behind it. According to this relation, we can say temperature and wavelength of radiation emitted by that hot body will be inversely proportional to each other. So according to visible light, WebCure, wavelength of violet is minimum and wavelength of red is maximum. So initially at low temperature, it will radiate maximum wavelength of radiation, that is red color. On increasing temperature, energy of body will also increase. So it will tend to radiate wavelength of smaller wavelength, radiation of a smaller wavelength. So color will change from red to orange, then yellow to green, and then blue, and so on, finally to black. In this way, its color of radiation or emission of radiation will change. So we may define this particular law as Main's displacement law. The maximum wavelength of radiation emitted by hot body is inversely proportional to its absolute temperature. It means this is wavelength versus temperature. So initially, let the temperature is this one, and further this is maximum wavelength and temperature of body at that part. Let's say this is lambda 1 and this is temperature T1. Temperature T2, lambda 2, and so on. So from this part, we can say T2 is small, so lambda 2 is large. T1 is large, so lambda 1 is small. So we can say lambda of maximum is inversely proportional to temperature of body. So product of lambda and T will be constant, which is denoted by B, which is equals to 2.29 into 10 to the power minus 3 meter Kelvin. It is equals to, or it is called Wien's displacement constant. Is it clear, Vifra?
Yes, sir.
Okay, just write it down.
Done, sir.
Now, related to this concept, there was a question in NEET. Three stars, P, Q, R, are radiating an orange, blue, green, respectively. Orange, their temperature of surface in ascending order. Try to solve. Good, Ifra. So in this part, we can say, according to Vibgyor, blue having maximum wavelength, then green, and then orange. So its temperature will be minimum. Then this star P having temperature, having radiation in orange color. So it will be TP. In green, star R, and in blue, star Q. So on the basis of name of star, relation of temperature will be this. Any doubt, Ifra?
No, sir.
So this is all about this entire chapter of thermal properties of matter. Okay. So we have just finished it. So let's stop here for today.
Okay.
We will cover that left out part, that is wave, with Aditi. Okay.
Okay, sir. And
Okay
sir, the
then.
chapters of term 1 which were left.
We'll
दूसरे
continue. We'll continue. We'll continue further.
okay.
Okay.